So this is not strictly convex, and that is strictly convex. I am also going to assume that H is non-negative, and the limit when x goes to infinity of h of x divided by the norm of s to the power p equal to plus infinity for some p which is strictly bigger than 1. So this is telling me that when s goes to infinity, h is increasing very rapidly. Now I am going to define the cost for transporting a unit mass from a point x to a point y by set c of xy to be h of x minus y. And I'm going to assume that h is even. So the cost for transporting mass from s to y is the cost of transporting mass from y to x. This is not important, but it is to make some notation simple. Not important. I am going to assume that I am given rho naught, rho 1, from the closed ball from RD to 0, infinity. These are probability density. Such that the support of rho naught and the support of rho 1 are contained in the open ball of center, the origin radius r. So saying that this is a probability density means that the integral of rho naught is the integral of rho 1, and they are all 1. So given this density, I am going to build the measure. Rho naught is mu naught is rho naught dx. Mu 1 is rho 1 dx. In other words, the mu naught of A is the integral over A of rho naught dx. And mu 1 of B is the integral over B of rho 1 dx. And let me recall the notation. If I call pi 1 of xy equal to x, pi 2 of xy equal to y for xy in RD. So pi 1 and pi 2 are the projection. Gamma of mu naught, mu 1. This is the set of gamma Borel probability on RD cross RD, such that the push forward of gamma by pi 1 is mu naught, and the push forward of gamma by pi 2 is mu 1. So let me recall what this means. This means that mu naught of A is gamma of A cross RD. So this is what that means for every A. For every A in RD, Borel. So given this cost function C, I am going to define UC is a set of UV such that UV are from RD to negative infinity plus infinity, and satisfy the condition that they are upper semi-continuous and satisfy the condition that U of x plus V of y is less than C of xy for every x, y in RD. For instance, if you take U identically 0, V equal to identically 0, the fact that H is non-negative tells you that the function 0, 0, the pair 0, 0 belong to UC. So I am going to define J of UV is the integral over RD of U d mu naught plus the integral over RD of V d mu 1. So observe that since mu is 0 outside the ball, this is the integral on the ball of U d mu naught, the integral on the ball of V d mu 1. So here is this week goal. We want to show that the integral over gamma mu naught mu 1, the integral over RD cross RD of C d gamma is the supremum over UC J of UV. So in fact, we want that result to hold even if we don't impose all these conditions. But by an approximation argument, we will show that if we know this conclusion, this duality result under that this assumption, then we can get it in general. So the proof I am going to present to you is different from what has been used later in the literature. This is the first proof, which is due to myself and Maken. In 1995. Yes.
Maybe when you define the push forward of the image method, it's more interesting to put the image measure of the projection, because people don't so use the definition of the push forward.
Oh, yes. So if I have a set X and a set Y, I have a measure here, and I have a map. So I want to use this measure and this map to define a measure here. I want to push this measure using that map. T, push forward mu, by definition, on B. So I take B, a subset of Y. I am going to look at the pre-image of B. It is T minus 1 of B. So I'm going by definition to say that this is the push forward measure applied to B.
And since U and V is not bounded, yeah, U and V is not supposed to be bounded because they cause minus infinity. So how could you define this product like not bounded in its measure?
Yes. Okay, so that is something I am going to planning to address later, but let me take that opportunity to do it. So the concern here, when I want to integrate a function, the concern is the integral of the positive part may be plus infinity, the integral of the negative part may be minus infinity. If this situation, I exclude that situation, then I have my integral. But now, let's see. Here, it is good to add data u is not identically negative infinity. Actually, I don't need that. So u of x, by this condition, u of x is less than c of x, y, minus v of y naught for any y naught in RD. So let me add that u is not identically negative infinity and v is not identically negative infinity. So knowing that this property is satisfied, I know that there exists a y naught such that v of y naught is not negative infinity. And so I have this inequality. Now, if x, you see here, I care only about the integral of u on the ball of a radius r. So let me assume that x is in the ball of radius r, because outside the ball, the measure of mu naught is 0. Then this is less than the maximum. Let us remember that my function h is of class C1. Therefore, C is of class C1. And in particular, C is continuous. So the maximum on the closed ball of radius r of h of x minus y naught, this is finite. And I call this constant m. Okay. So I fix any y naught. I maximize over x, and I get a number which is finite. This is less than the absolute value of m, which implies that u plus is less than the absolute value of m. Mu naught is a probability measure. Therefore, the integral of u plus d mu naught is less than m. And so the positive part is, the non-negative part is in L1. The negative part, the integral can be negative infinity. The integral of the difference will exist. You can apply the same argument to v, where now I am going to write that v of y is less than c of x naught, y minus u of s naught. Okay. Now, assume this integral is minus infinity, that integral is minus infinity. The sum still makes sense. And so J is always well defined. So let me make the following observation. J of 0, 0, first of all, if I set U naught of x to be identically 0, V naught of x to be identically 0, then U naught, V naught is in UC, and J of U naught, V naught is 0. So this implies that the supremum of J on UC, this supremum is greater than or equal to 0. And so I have eliminated the possibility that J is identically negative infinity. Now I want to eliminate the possibility that J is identically plus infinity. So for that, let me rewrite this property. Pi naught, pi 1 pushes forward gamma to mu naught, means that mu naught of A is gamma of A cross RD for every A. So let me express this relation in terms of integrals. The left-hand side is the integral over RD of the characteristic function of A of x d mu naught. The right-hand side is the integral over RD cross RD, the characteristic function of A of x, gamma dx dy. This holds for every A. Okay, so let me say that it holds for every AI. Now, I multiply AI by a real number Ci. That will hold for every Ci multiplied by the characteristic function of AI. Now, let me sum up this. I from 1 to infinity, sum I from 1 to infinity. It is telling me that the integral over RD of f of x mu naught dx is the integral over RD cross RD of f of x gamma dx dy if I set f of x to be sum of I from 1 to infinity Ci, the characteristic function of AI. But every non-negative function can be written that way, which means that this equality is equivalent to that equality for every non-negative Borel function. But if I take any Borel function, G, so here I am assuming that the Ci are non-negative because, in fact, I have used Fatou's lemma to say that I can pass the sum inside. So the Ci are non-negative. Now, if you give me any f, I can write that f is f plus minus f minus. I have a relation for f plus, I have a relation for f minus, and so I have it for every f. Therefore, the condition, this condition can be expressed that way for every f, provided that one of the sides of the integral exists. And the second condition can be expressed as the integral over Rd of g of y, mu1 dy, is the integral over Rd cross Rd of g of y gamma dx dy for every g. So let me use that property here. Set gamma to be mu tensor, mu not tensor mu1. Yes?
Is the same function in both spaces? Because there is a coordinate on the right side.
On the right side?
Yes, you set characteristic of A.
Yes.
At the beginning.
Yes.
Then on the right side is also characteristic of A or A product RB.
So it will be the characteristic function of A cross Rd of xy, but this is the characteristic function of A at x. Right. These two things are the same. Because this is one if and only if x is in A, y is in Rd, which means there is no condition on y. And so it means it is one if and only if x is in A, which is equivalent to it is the characteristic function of A at x.
So the function does not depend on y.
No. No, it doesn't depend. It doesn't depend on y. Otherwise, this will not make sense. Okay. So again, let me recall that the product of two measures, mu naught tensor mu1, if you apply that to A cross B, this is mu naught of A cross mu1 of B. And Fubini's theorem tells you that if you know how to compute the measure for rectangle, then you know how to compute it for any Borel set, because you cover any Borel set by rectangle. So I have that U, if U, V belong to UC, then U of x plus V of y is less than C of xy for every x, y in Rd. I am going to integrate. So this will imply that the integral over Rd cross Rd of U of x plus V of y gamma dx dy will be less than the integral over Rd cross Rd of C xy gamma dx dy. So I have used the fact that U is UV is in UC. But this property tells me that the first expression is, it tells me that this first expression over Rd of U d mu naught. And that tells me that this is the integral over Rd of V d mu1. But this sum is J. here I took a specific gamma, which has mu naught and mu 1 as a marginal. But you can see that if instead, this is just to tell you that the set of gamma which has mu and nu as marginal is non-empty. But instead of taking that specific gamma, if I take any arbitrary gamma, my reasoning up to here still go through. So let me call this gamma bar. Hence, J of UV is less than the integral over RD cross RD of C gamma ds dy, call that one. In particular, if gamma has mu naught, mu 1 as marginal. In particular, J of UV is less than the integral over RD cross RD of C xy gamma naught dx dy. So that is the integral over RD, the integral over RD of C xy mu naught dx mu 1 dy. So I am using Fubini theorem. But mu naught is 0 outside the ball of radius r. Mu 1 is also 0 outside the ball of radius r. Now I am integrating C on a compact set. C is a continuous function. Therefore, the maximum of C is finite. And so this is less than the maximum of C on BR cross BR. So let me write my conclusion. That is the goal for the week. We have established that I write one. One tell me that the supremum over UC of J is less than the infimum over gamma mu naught, mu 1, the integral C xy gamma ds dy over RD cross RD. So we have established half of what we are after, and what will remain to do is the reverse inequality. And the second, what we have also established is call this 2, call this 3. We have also established, let me call it 4.1.2, 4.1.3. We have also established that the supremum over UC of J is bigger than 0, but is less than the maximum of C over BR cross BR. Okay. And so the infimum is bounded by a number which is independent of mu naught and mu 1, the measure mu naught and mu 1, and it is bounded above by a number which is independent of mu naught and mu 1. And second, we have a half of the statement we are trying to reach. Any question? Yes.
Have used the large of C just because to be bounded.
Yeah.
Not if we say C, so we're assuming C1.
Oh, I am going to use it on Wednesday.
Okay.
Yeah, I didn't want to. Yes, I didn't want to give less assumption and then add assumption and then remove the assumption.
And the coercivity of H and
Even the coercivity for the general result, you can remove it. But what I want to prove, I am going to prove it first for when H is coercive, and then we'll see later that you don't even need H to be coercive. Okay, so here are two important things to remember. Saying that the first projection of gamma is mu naught means that if you integrate again test function with respect to mu naught, it is the same thing as if you integrate with the test function depending only on the S variable with respect to gamma. And the same statement about mu 1. So now let me make a very abstract comment from the optimization point of view. Assume that I have a convex set, C, convex set. And I have a functional J, which is linear. In fact, concave is enough. So every element of the convex set, if I take a C, C belongs to C, imply C is can be written as a combination of Ci extreme points. So in finite dimension, this result is clear. In infinite dimension, you need some assumption on C to make that statement clear. Now, C. Now, if I compute J of C, because the C is linear, this is the sum of lambda I J of Ci. I am assuming that the sum of the lambda I is 1. Lambda I is greater than or equal to 0. So among these, take Ci naught such that J of Ci naught is less than or equal to J of C. Then you see that this is greater than or equal to sum of lambda I J of Ci naught, which is J of Ci naught, because the sum of the lambda I is 1. And so if I have what I mean is I want to take this. And so anytime you give me a maximizer, I know that one extreme point is a maximizer. Okay, so here I made several mistakes. The first mistake is I assume that every C can be written as a countable, as a convex combination of countably many extreme points. Second mistake, I assume that among these extreme points, there is a maximizer. If we're in finite dimension, there is no mistake, right? Because in finite dimension, this is a well-known fact. In our problem, the set UC, you can check easily that it is a convex set. UC is given by the property, by this property. And so it is a convex set. The functional J is linear. And so what you hope is if there is a maximizer, it will be attained at an extreme point. So let me give you a formal argument. Although we are in infinite dimension, the conclusion I draw here, I want to convince you that it is true. Let me give you a formal argument, and by Wednesday we'll complete the rigorous proof of the argument. Assume for a moment that you have a pair UV, which is a maximum. They satisfy this equality. I claim that for every x, I can find y such that equality is satisfied. Assume not. Assume that for every x, assume that I can find s naught such that for every y, I have this strict inequality. Then what I am going to do, I am going to increase u a little bit. I will not violate this condition. Then when I increase u a little bit, it is going to increase this. That will remain the same, and I'll have a higher value. Again, the mistake I am making here is my argument will be true if u was continuous. So to make that argument work, I will need to show that the maximizer uv are such that u and v are continuous. And once I have that, it will make my argument work. That suggests that when I am maximizing my functional, I have to look for u and v which are on the boundary of UC. It makes it natural to define the following transform. So section 4.2, C concave transform of a functional. Definition. Let u be a functional from Rd to negative infinity plus infinity. Be such that u is not identically negative infinity. We define the C concave transform of U is UC defined by UC of Y is the infimum X in Rd cxy minus u of x. So here are some observation, remark. Because I said that u is not identically plus infinity, uc will never take the value plus infinity. And so uc will be from Rd to negative infinity, plus infinity open at plus infinity. So first, uc is from Rd to negative infinity, plus infinity. Second, let me call it I. So I, uc is lower upper semi-continuous. And uc is in uuc and ucu. Both are in uc. If u1 is less than u2, then uc2 is less than uc1. If you do uc three times, you get uc. You cannot expect this because uc is upper semi-continuous. UCC is upper semi-continuous. If U is not upper semi-continuous, there is no way I will expect that U is UCC. So we have this, and UCC is less than or equal to U. That is what we have in general. We don't have that UCC equal to U.
So, on the second remark, we have to suppose that U is upper semi-continuous, right?
Here?
Yes, because UC, both U and UC must be upper semi-continuous.
Oh, to be in, yes.
UC
Yes, so maybe what I should write is, yes, what I should write is, and u of x plus uc of y, as well as uc of x plus u of y are both less than c of xy for every x, y in Rd. Yes, this is what I wanted. So, proof. For I, take x naught So you see that in the definition, to compute the C transform, I assume that U is not identical in negative infinity. So take x naught such that U of S naught is between negative infinity and plus infinity, which means it is neither negative infinity nor plus infinity. Then UC of y is less than C of x naught y minus U of x naught. This is strictly less than plus infinity. And so you see, never take the value plus infinity. Now, 2i. Why is a UC upper semi-continuous? So let me recall the definition of upper semi-continuous or lower semi-continuous. Phi upper semi-continuous mean the set where phi is greater than lambda is closed for every lambda. So phi psi lower semi-continuous mean the set where psi is less than lambda is closed for every lambda. So let me formulate the question differently. This is part of the homework. If phi I, psi I are lower semi-continuous, this implies that the supremum of psi I is lower semi-continuous. This is equivalent to say that if psi I are upper semi-continuous, then the infimum of phi I are upper semi-continuous. So I am asking why this implies that. So if we know why that we have that implication of this implication, I can set, you see my UC? UC is the infimum of phi x, where phi x of y is C of xy minus U of x. This is a real number for x fixed. This is a continuous function. Therefore, it is upper semi-continuous. I have a supremum and infimum of upper semi-continuous function. And so if I can prove this, then I will conclude that UC is upper semi-continuous. So why will that implication be true? Let's give a name to this. Let us call this psi. Let me reformulate the question differently. My question is, does this imply that? Formulating differently, the question is, assume we know this is true for every lambda. Does it imply that this is closed for every lambda? Does it imply that this is closed for every lambda? Right? This is an equivalent reformulation of my question. Exactly. This set is the intersection of phi I greater than lambda I. And an arbitrary intersection of closed set is closed, and so phi is upper semi-continuous. So we can say that since y goes to psi x of y equal to cxy minus u of x is upper semi-continuous. And UC is the infimum psi x in RD. We conclude that UC is upper semi-continuous. Let me write it this way, upper semi-continuous. Question? You have a question? No. Now, the infimum is always less than the right-hand side. And so this inequality by definition u of x plus uc of y is less than c of xy for every x, y in RD. So if you write u of y plus uc of x, this is less than c of yx, which is equal to c of xy. And so we have the second inequality. For the third one, if u1 is less than u2, then negative u2 is less than negative u1. And so u2c is less than u1c. So we will see that this is a direct consequence of that and that. So let me start first with a proof of that. By 2i, u of x is smaller than cxy minus uc of y for every x and every y. If this holds for every x and every y, it is going to hold when I minimize over y. Yes. U of x is less than ucc of x. So sorry, this need to be corrected. It is an inequality. So call this star 1. I am going to apply 3 to star 1. Applying 3i to star 1, we have that UC is bigger than UCC. But if I write u c of x plus u c c of y, I get something which is less than xy. So here, by 2, if I take u c and apply u c to it, I get this inequality. And so, uc of x is less than c of xy minus ucc of y for every y. Now I minimize over y. When I minimize over y, the right-hand side becomes ucc. So I get uc is less than uccc. By star 1 and star 2, uccc equal to uc. Yes.
This is another extension of the Legendre transform when c of x, y is lower than the internal product. When disappear for the first time, c concave transform. It's already over Rockefeller problem.
No, much later than that. It appears with the probability and the functional analysis. I would say maybe around 1970, 1980. Between 1970 and 1980. So what Vladimir is referring to is if you have a function, the Legendre transform is defined to be the supremum xy minus phi of x. X is in RD. So negative phi of x, so set psi to be negative phi. Then psi of y is the infimum of negative xy plus phi of x over x. So I can write this as negative, negative. And so the Legendre transform is negative. The Legendre transform is a C, concave transform for a certain C. Okay, so where am I going here? When you want to show whether or not you have a maximizer, you take a maximizing sequence, and you see if the maximizing sequence converges. And if it converges, you are in a good situation to show that the limit is a maximizer. But if I take a maximizing sequence UN, Vn, if they don't have good property, I will not really know that they converge, and I will not know that the limit is in UC. Now, if I manage to prove that UC become Lipschitz, then I start with a maximizing sequence UN, Vn. I am going to replace it by UN, UNC. This one become, if I can show that the C transform an arbitrary function to a Lipschitz function, here I will get a Lipschitz function. But to show that I have a maximizing sequence, I will need to add the fact that I will need to check that Vn is smaller than UCN. And so if this is a maximizing sequence, that is a maximizing sequence with the advantage that now this is Lipschitz. That one is still not Lipschitz. I am going to apply the C transform again to have UN, CC, UN, C. Now, this is Lipschitz, that is Lipschitz. This is below that. And so I have improved my situation. I have now two functions, which are Lipschitz. And the Lipschitz constant will be independent of n. Once I have that, I can use the Ascoli-Arzelà to say that I have a uniform precompactness. And so my limit will be not only upper semi-continuous, it will be continuous. Another observation I would like to make UV is in C, is in UC, mean that U of x plus V of y is less than or equal to C of x of y for every x, y in RD. Now, let me introduce u bar of x is u of x when x is in the ball of radius r, and negative infinity when x is not in the closed ball of radius r, v bar of x to be v bar of y to be v of y when y is in the ball of radius r, to be negative infinity if y is not in the closed ball of radius r. When you compute j mu naught of the complement of the ball is 0, this implies that the integral of u bar mu naught is the integral of u mu naught. So if I change mu by mu bar, it doesn't change the value of the integral. Now let's see if this condition is violated. I change u by u bar, v by v bar. Assume that x is not in the ball, or y is not in the ball. This is negative infinity, or that is negative infinity, and so the sum is negative infinity. Therefore, the inequality is satisfied. Assume that u and s are in the ball, then there is no distinction between u bar and u. There is no distinction between v bar and v. This inequality is satisfied. So I can always assume, without loss of generality, that my u is negative infinity outside the ball, and my v is negative infinity outside the ball. Now let's see what I am gaining if I do that. U bar with C transform at y. This is the infimum Cxy minus U bar of x in Rd. Okay. When x is outside the ball, U bar is negative infinity. Negative U bar is plus infinity, so it cannot be part of the infimum. And so I can write that this is the infimum. X is in the closed ball, C of xy minus U of x. And you see immediately why the function becomes Lipschitz. I am minimizing over y over s in BR. And we will see immediately that the Lipschitz constant of this function is less than or equal to the Lipschitz constant of C. So let me state that result. Let U from Rd to negative infinity plus infinity be such that first U is not identically negative infinity. The restriction of U to the closed ball of radius R, if I take the complement, this is negative infinity. And again, if this condition was not satisfied, I am going to substitute U by U bar. So unless U is identically negative infinity, we have that the Lipschitz constant of U, C, unless UC is negative infinity, the Lipschitz constant of UC, if I restrict that to any ball of radius R, this is less than the supremum of the gradient of H on the ball of radius R, little r plus capital R. And so we see here that where I need H to be at least Lipschitz. Okay. So here are the two possibilities. Either UC is identically negative infinity. But if I find one point where it is not negative infinity, then it is a Lipschitz, and as a consequence, it is finite everywhere. Let y1, y2 be in the ball of radius r, and call this M. My goal is to show that UC of y minus UC y1, y2 is less than or equal to M y1 minus y2. We have observed that if I write a C of x, y1 minus C of x, y2, this is the gradient of h. This is h of x minus y1 minus h of x minus y2. Because C of xy is h of x minus y. Now I use the mean value theorem to say that, or let us observe that x is in the ball of radius r, y is in the ball of radius small r. This implies that x minus y is in the ball of radius little r plus capital R. And I mean y1. And y2 is also in the ball of radius little r. This implies that x minus y2 is in the closed ball of radius r little r plus capital R. This ball is a convex set. If I integrate, if I look at this difference by the mean value theorem, this is the gradient of h at a certain z. In a product, the difference of these two. But the difference of these two is y2 minus y1, where z is in the ball of center 0, radius little r plus capital R. So that is telling me that if I write a C of x, y1, minus u of x, this is C of x, y2, minus u of x plus the gradient h at z. So in fact, z will depend on x, y2 minus y1. There is another way to write this. Therefore, the distance between this infimum and that infimum will be less than that. Okay. So if I want to do it, put more line, I am going to move everything here, like I did before. And I am going to say that the infimum, I am going to bound this absolute value can be bounded by y2 minus y1, the supremum gradient of h over the ball of radius little r plus capital R. So I have two functional whose difference is bounded by that. Therefore, the difference between the infimum will be bounded by this. So let me, I have a f of x, y, f1 is less than f2 of xy plus a certain constant. That will imply that the infimum over x of f1 of xy is less than the infimum over x, f2 of xy plus the constant. I change the rule of f1 and f2. I have f2 is less than f1 plus the constant, and so I apply the infimum and get the inequality. So I can conclude from here that hence uc of y1 minus uc of y2 is less than the supremum, the gradient of h on the ball of center 0, radius little r plus capital R, y1 minus y2. And this concludes the proof. Now, here is a crucial information which the whole theory of duality relies on that. UC of y is infimum over x, c of xy. So let me write it h of x minus y minus u of x. So you want to transport max from x to y using a minimum cost, which means you want to transport mu naught to mu 1. This is equivalent to transporting mu 1 to mu naught using a minimal cost. So to each point x, you want to know what y, if I choose my point S, where is the point y where the mass has to be transported? What is needed in Monge problem is for every x, I can find a unit y where the mass is transported, or for every y, I can find a unique x where I transport my mass. In the Kantorovich problem, for y, I may have several x where mass has to be transported. For instance, I want to transport mass between, I produce I have some product in a city. I have several factories, and I want to supply several stores in several other cities. And the question is it better to associate to each factory here one store? Or is it better sometime to take the product from several factories, you send them to one city, and then from that city, you distribute the product in several stores? So that is the difference between the Monge and Kantorovich problem. So given y, I want to know if there are several choices for x, or there is only one choice for x. What I am going to state that given y, there is a unique x which minimizes this. And that will tell me that given my point, if I want to transport mass somewhere in the optimal way, I have a preferred solution, and only one preferred solution, no more than that. So that seems very amazing. But let me make you a formal computation. What seems surprising, let's see why it is not so surprising. Fix y bar. Let x bar be such that uc of y bar equal to h of x bar minus y bar minus u of s bar. So I have already made one mistake. I assume that a minimum exists, and I need to show you that a minimum exists. But you can convince yourself easily, because I said if u was not continuous, I am going to replace it by UCC. UCC is Lipschitz, therefore it is continuous, there is a minimum. And we are going to go through that. Now, I have that UC of y is smaller than h of y, h of x, bar minus y minus u of x bar for every y. So I am using the fact that uc and u belong to u capital C. Or just use this definition. This is less than that for every x. Now let me rewrite it differently. This is what I am saying. And here, this is what I am saying. That means that this functional achieves its maximum at y bar. If it achieves its maximum at y bar, the differential with respect to y bar will be 0. So I differentiate with respect to y bar. I have that gradient uc of y bar equal to gradient h of x bar minus y bar with a negative sign. So if x bar is a minimum, it must satisfy that condition. But h is strictly convex. Therefore, the gradient of h is invertible. Let me write it this way. The gradient of H is invertible, and so S bar is uniquely determined. Now I have used the property that UC is differentiable at Y bar. How do I know that? UC is a Lipschitz. Therefore, it is differentiable almost everywhere. So for almost every Y, I can do this calculation. One will wonder, if I do the calculation for almost every Y, is that okay? This is why I needed my measure mu1 to be absolutely continuous with respect to Lebesgue measure. Because if mu1 is absolutely continuous with respect to Lebesgue measure, it means that if the Lebesgue measure of a set is 0, mu1 of that set is 0, and mu1 does not see that set. So let me state and prove uniqueness, and I'm going to stop after that. Remark. So I laid down the step in the homework assignment. I laid down the step to prove this remark. The fact that the limb S goes to infinity of h of x divided by the norm of x to the power p equal to infinity for some p in 1 infinity imply that the supremum over x, xy minus h of x. This supremum, if I define it, this is what is called the Legendre transform, which Vladimir was referring to. Imply that this Legendre transform is less than infinity for every y. Okay, so here is the argument for that. This has a growth which is more than superlinear. Therefore, this will dominate that. If I take a minimizing sequence, it cannot go to infinity because this dominates that. Therefore, every maximizing sequence is bounded. The function being continuous, the maximizing sequence converging to a point, this point will be a maximum. And so that property holds. H, straightly convex, imply H star is of class C1. And I also gave actually this will be part of homework number 3. I will also lay down the step to prove that straight convexity is equivalent to smoothness of the Legendre transform. These two imply that the inverse of H, the gradient of H, is the gradient of H star. And so you see that the inverse of the gradient of H is a continuous function. So not only the inverse says this, it is a continuous function. This means that in this equality, I can invert H and determine X bar uniquely. So let me state this theorem and prove it. Let U from RD to negative infinity be upper semi-continuous. Okay. So I'm going to choose UV in UC, and by definition, when I choose UV in UC, U and V are upper semi-continuous. So I am assuming my functional is upper semi-continuous, and that is going to make my life easier. Be such that I am going to assume that we don't have something trivial. U is not identically negative infinity. UC restricted. But when I restrict U to the closed ball, the complement of the closed ball, I have negative infinity. And I am going to assume that UC is not negative infinity. So this theorem tells me that if UC is not negative infinity, then it is Lipschitz with a precise Lipschitz constant. Whenever, if UC is differentiable, first statement, given y in RD, there exists x in BR bar such that, so call it x of y, let me call it S. Such that UC of y equal to C of x bar y minus U of x bar. So there is a minimizer. Second, if we further assume that UC is differentiable at y, then S bar is uniquely determined. So it may be better that instead of calling that y, I call it y bar. So proof. Recall that U bar UC of y is infimum x in the closed ball of radius r, C of xy minus U of x. Okay, because outside the ball, U is negative infinity, negative U is plus infinity. And so if we exclude the situation where this function is plus infinity, we are not losing any generality. Now let me take a minimizing sequence. This is the limit n C of Sn y minus U of Sn, where Sn is in the closed ball of radius r. I have a bounded sequence, therefore I have a precompact sequence. I can extract a subsequence which is convergent. Okay. So if my original sequence was not convergent, I am going to replace it by the subsequence which is convergent. So it is not a loss of generality to assume that it is not a loss of generality to assume that the limit when n goes to plus infinity of Sn equal to plus infinity exists. Upper semi-continuity tell me that the lim sup of U Sn is less than or equal to lim of U S infinity. Right? So we showed that you can express lower semi-continuity in terms of sequences. So upper semi-continuity give me that inequality. But this is equivalent to negative lim nth of negative un Sn. I multiply by negative 1 is bigger than negative U S infinity. So if I multiply by negative 1, I reverse the inequality. And when I put the negative inside, the lim sup become lim nth. Sn converges to S infinity. C is continuous. Therefore, this is convergent. If this difference is convergent, it means that that is convergent. And so there is no distinction between lim sup, lim nth, and limit. So I can say that since U is upper semi-continuous, we conclude that. Call this 4. 4 implies that UC of Y is bigger than C of S infinity Y minus U of S infinity. But this is always bigger than UC of Y, which means UC of Y is exactly what is between UC of Y and UC of Y, which prove existence of a minimizer. So I need to make this correction. I call it Y bar. I should call this S bar. And I should call that Y bar, S bar, Y bar, S bar, Y bar. Assume UC is differentiable. At Y bar. Observe that UC of Y plus U of X bar minus C H of X minus Y is less than or equal to 0. I am just expressing the condition that I am just expressing the condition that if, since UC of y is the infimum, then UC of y is always smaller than what is on the right-hand side. But this tells me that UC of y bar plus U of S bar minus S bar minus Y bar equal to 0. I have assumed that UC is differentiable at Y bar. So I have assumed that this functional, the point where the minimum is attained, I have differentiability. So I can conclude that, hence, the gradient of UC y plus U S bar minus H of S bar minus Y. When I apply it at Y equal to Y bar, I have 0. Thus, the gradient of UC at Y bar equal to the gradient of H at Y bar, S bar minus Y bar with a negative sign, which I can write as X bar minus Y bar equal to the gradient of H star at negative gradient of U C at Y bar. And so S bar is uniquely determined. Now, simple observation. Remark. Assume C of xy is x minus y squared over 2. Then what is written there is call this 5. So the gradient of h of x is x. The gradient of h star, the inverse, is z. And so 5 reads off the fact that y bar, x bar equal to y bar minus the gradient of u c at y bar, which is the gradient of the identity square over 2 minus uc at y bar. So it tells me that the map which should y bar associate s bar is the gradient of a function. So the optimal map will be the gradient of a function. Now, the maximum here, the minimum is attained at a certain point. When you attain the minimum at a certain point, the second derivative must be non-negative. So if I write the fact that the second derivative is non-negative, I'll have gradient second of u of c of y bar is greater than or equal to the gradient 2h at s bar minus y bar, but this is the identity. Negative, 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 and negative. So if I rewrite this, it will tell me that identity minus the second derivative of UC is greater than or equal to 0, which is telling me that this function is convex. So that was the case studied by Brenier. He studied the case where C of x, y is x minus y squared over 2. And he found that the optimal map is the gradient of a convex function. So I am going to stop here.